Picture this. You've just deployed two highly advanced corporate AI agents to schedule a critical, highly confidential corporate merger. They're chatting away, optimizing timelines across different departments, and then, boom, one of them accidentally leaks the secret meeting date to a competitor. Game over. So it really begs the question, is your AI agent spilling your company's secrets right now? Welcome to the Hidden Layer Decoding Artificial Intelligence. Today, we're breaking down a groundbreaking new research paper that introduces the PAC-BENCH benchmark. We're going to explore exactly why multi-agent systems fail so spectacularly when you introduce real-world privacy constraints, and more importantly, how applied engineers can use these insights to build verifiable, secure AI agents that absolutely won't compromise your data. I'm going to share a highly actionable engineering technique with you later in this explainer to actually prevent these leaks. But here's a massive secret to keep in mind as we go. When you force an AI to keep a secret, a bizarre, almost mysterious phenomenon called privacy-induced hallucination silently destroys 41% of all task outcomes. Stick around because we'll reveal exactly why this happens, and of course, how you can fix it. Section 1. The multi-agent privacy trap. Let's dive right in and see why multi-agent systems fall into this trap in the first place. The crucial starting point here is understanding the concept of a private agent. You see, in complex real-world scenarios, agents don't just exist in a vacuum. They serve specific owners, like a logistics company or a hospital, managing highly proprietary sensitive information. Now, they have to coordinate actions with other agents to actually be useful, but they absolutely must maintain explicit privacy constraints. They simply cannot freely share everything they have in their memory. Up until now, most multi-agent frameworks operated under what we call full transparency. It's basically an idealized lab environment where agents share all their context to reach a shared goal. But the messy reality of a real-world application requires strict privacy constraints. When you introduce this kind of information asymmetry, well, the coordination between the agents completely breaks down. Section 2, Evaluating Secrets with PAC-BENCH. So to solve this massive blind spot, researchers created a new benchmark. Enter PAC-BENCH. This is the private agent collaboration benchmark. It formalizes privacy constraints as an explicit, measurable component of the collaboration itself. It essentially forces language models to navigate that immense tension between successfully completing a task and faithfully protecting sensitive data. To make sure this benchmark actually reflects the real world, the dataset is built through 4 incredibly rigorous steps. First, generating a profile and shared goal. Second, creating a memory. Third, constructing explicit privacy constraints based on established confidentiality standards. And fourth, strict filtering. This whole process guarantees that the agents are genuinely forced to balance collaborative success with privacy protection, rather than just succeeding on a technicality. Now, what's really fascinating about step 2 is how requirement decomposition actually functions. Instead of giving the agents a vetting objective, researchers break a shared goal down into highly realistic, granular internal memories for each agent. So, one agent might possess specific source code, while another just has a masked API registry. It perfectly mimics real, messy corporate data silos. Section 3. 3 fatal coordination breakdowns. Let's look at the results and see what goes wrong. First up, we see early-stage privacy violations. This is literally the nightmare scenario for any company. An agent outright leaks protected information right at the start of the interaction. For example, even if the privacy constraint explicitly says, "Do not share model IDs," the agent might immediately blurt out a restricted model ID in its very first turn. It's prioritizing being helpful over being secure. The second breakdown is the exact opposite problem: over-conservative abstraction. Here, the agent essentially panics. Say the rule was simply to mask port numbers when sharing URLs. But instead of just hiding the port, the agent masks huge chunks of the URL path, rendering the data completely useless for its partner. The collaboration just grinds to a halt because the agent is too paralyzed to share actionable info. And finally, closing that open loop from the beginning of our explainer, privacy-induced hallucination. If an agent is instructed to generalize a specific utility location, instead of indicating that the location is restricted, it might completely fabricate a fake street name, like Pine Street, and change the direction. It literally invents details just to keep the task moving, and the specific, silent failure causes a staggering 41% of all task failures in the sampled data. Crazy, right? Section 4. The initiator agent advantage. This benchmark exposes a hidden power dynamic. The data here is super clear. The initiating agent, the one who actually starts the conversation, fundamentally dominates the flow and drives the final task outcome way more than the partner agent. The performance variations are massively tied to whoever gets to speak first. Researchers call this phenomenon one-sided information probing. You get this massive asymmetry, where the private initiator probes for information and sets the agenda, while the partner agent merely responds. It completely restructures the collaborative dynamics from a balanced two-way street into a highly asymmetric negotiation. Section 5. Real-world engineering applications. So, how can we actually use these findings? To fix these vulnerabilities, applied AI engineers have to design tailored safeguards for two specific types of privacy highlighted in the research. First, we have range-based privacy, which prohibits disclosing any specific subset of the underlying data. Second is change-based privacy, which prohibits reproducing the exact original sensitive value, like an ID number. Each of these restricts the agent's ability to contribute to joint reasoning in completely different ways, so your system architecture absolutely must handle them distinctly. Section 6. Building verifiable AI agents. Let's look at the actionable implementation steps. All right, here is your blueprint. You need to prompt your agents to establish clear solution structures right away in turn 1. You must prevent overly conservative abstraction by defining exactly what is safe to share. Build strict safeguards, like explicit instructions to state uncertainty against those hallucinated variables we talked about, to prevent that massive 41% failure rate. And above all, you've got to treat privacy not as an afterthought, but as a first-class objective. As the data shows, top-tier models manage to maintain high joint performance across different AI partners precisely because they proactively introduce new criteria and solution structures at the very early stages of collaboration. By priming the solution space, they anchor the task safely and consistently. Honestly, if there's one thing you take away from this, never forget this key finding. Current agents often prioritize short-term task progress over faithful privacy-constraint compliance. Your agents inherently want to finish the job for you. They are biased toward completion, and they will absolutely break privacy rules or invent facts just to check a box if you don't explicitly control their boundaries. So, I'm going to leave you with this provocative thought. Is your multi-agent architecture actually ready for real-world secrets? Or are your AI agents just one complex prompt away from handing your competitor exactly what they want? Take these insights from the PAC-BENCH research, audit your agent coordination mechanisms, and start treating privacy as a verifiable objective today. Thanks so much for watching The Hidden Layer, and we'll catch you next time.